And so, all right, here we go. We're looking at last night's homework where we learned the rat root theorem, or rational zero theorem, right? Or rational root theorem, whichever you want to call it. And here's a particular problem, and I'm going to incorporate all of our analysis. So I'm going to use Descartes. I'm going to use fundamental theorem of algebra. So I'm expecting that there are 3 answers to this problem, right? So let's figure this out. So let's see. Our p is the 9, right? So our possible p's are the factors of 9. So that's like plus or minus 1, plus or minus 3, and plus or minus 9. And our q is the 2. So the factors of q are plus or minus 1 and plus or minus 2. So what the rational root theorem said is that if I have rational x-intercepts, or rational roots, or rational zeros, all right, those 3 are pretty much synonymous, that it will be the ratio of p over q, where p are the factors of the constant and q are the factors of my leading coefficient. All right, so I've narrowed my list down to a finite search. All right, so let's see. The other thing I'm going to do is Descartes, my little plus minus I chart here, where the types of x-intercepts or roots can be determined based on the sign changes in the function. So from 2 to negative, positive 2 to negative 11, that's 1 sign change, 2 sign changes. So that's a total of 2 positive possible that I'm expecting to see. And then I need to find h of negative x. So if I plug in negative x for all of these, so negative x cubed would be negative, so that's negative 2x cubed. Negative x all squared is positive, times a negative 11 is still negative, so negative 11x squared. And 12 times negative x is negative 12x, and then plus 9, let's see. And if I count the sign changes here, none, none, and 1. So I'm expecting as many as 1 negative x-intercept. And like I said a moment ago, I know that there will be 3 total exactly. So 2 plus 1 is 3, so there would be 0 imaginary roots in that situation, right? Now what's the other possibility that I could have? 0, 1, 2, right? Because I can reduce either the positive or the negatives by an even number, right? So 2 minus 2 is 0. I can't change the number of the negatives, so these are my 2 possible situations. I know that there will be at least 1 negative answer and possibly 2 or 0 positive answers. All right, so that's going to help us narrow down our search. So let's do some synthetic substitution here. So let's see, I don't need any placeholders. So 2, negative 11, 12, and 9. And let's see, hopefully my basic arithmetic skills are better today. And I don't know. I'm always a fan of trying 1 first, if 1 is one of them, right? 1 over 1. So, right, so these are my p's over q's I'm putting here. So 1 over 1 is a possibility. Bring down the 2. 1 times 2 is 2. With a negative 11 is negative 9. So if you're just joining us here, I'm skipping some of the synthetic division steps. I'm doing some of that math in my head just to make it quicker. 1 times negative 9 is negative 9, plus 12 is 3, bless you. 1 times 3 is 3, with 9 is 12. So this remainder being 12 is not 0, indicating that 1 is not a root, so I need to keep searching. All right. So let's see. Would I try 2 next? Right. Yeah. The next one I might try is like 3 over 1. I mean, technically there's some numbers in between 1 and 3 here. I could try 3 halves, or I guess 1 number. But we'll try 3 first. Usually, I mean, if you want to avoid fractions first, you could, although that's not always guaranteed to be the most helpful strategy. So let's see, bring down the 2. 3 times 2 is 6 with a negative 11 is negative 5. 3 times negative 5 is negative 15. Oh, I'm feeling good about this one. I think it might work. Negative 15 and 12 is negative 3. 3 times negative 3 is negative 9 with a positive 9 is 0. So that means one of my answers is 3.
Yay, there's no imaginary numbers.
Oh, good analysis. I didn't even think of connecting it to that, right? So the fact that there's one positive answer means there will guaranteed be 2, and there are also no imaginary answers. So I'm looking for 3 real answers here. Now I do want to point out that these are the possible rational zeros. So rational numbers aren't all of the real numbers. There are also irrational numbers. So if I, for instance, had an answer that had like the square root of 2 in it, that could be invisible to our current search. All right, so this isn't guaranteed to give me all of the answers unless those answers happen to all be rational. Okay. So let's see. So let's. I guess now we know there's another positive answer, so we might as well try 9. All right, so I found one of the 2. And I guess I'll work with the depressed polynomial here. So I'll kind of narrow my search down, and I'm just using this row here now. So if you wanted, I could even write that depressed polynomial. I could call it g of x 2x squared minus 5x minus 3. And you wouldn't be wrong at this point just to take that and set it equal to 0 and factor to solve or use quadratic formula or whatever. That wouldn't be wrong. All right. I'm going to continue using the table because that's the new skill to us, and I want to have us be familiar with it. So let's try 9 here. So I've got, bring down this 2. 9 times 2 is 18. With negative 5 is positive 13. And then 9 times 13, 90 plus 117, yep. Minus 3 is 114. So my remainder is 114, which is definitely not 0. So 9 is not going to work. Now, actually, that's the other thing we can consider. What would the shape of this look like based off of the end behavior? I mean, if I look at the degree and the leading coefficient, what kind of swoop is it going to be? Is it going to be one of these or one of these? The second one, right? Because it's a regular positive leading coefficient. So I'm expecting that as I plug in bigger values of x, my y values will eventually just go off to infinity. All right. So, and I did just plug in my largest value, largest possible rational value. Anyway, so it looks like 9 didn't work. So what do you guys want to try next? What are your thoughts?
Well, you still have 3 halves to try.
Right, we have 3 halves and 9 halves.
We have a half too, don't we?
Oh, we also have 1 half. Yeah, you guys are right. Yeah, all sorts of things to try.
But isn't it this problem like the one that we did yesterday?
Oh, that's right. Could it possibly have 3 show up multiple times? That's always so sneaky. Because, yeah, I could end up trying all of those factors. I could try 1 half, 3 halves, 9 halves, and then not end up finding it, but still know that there's another positive answer. And that's why I guess typically once you get it down to a quadratic, it makes the most sense to just set this equal to 0 and solve. So you're anticipating that 3 might show up twice, is what you're saying?
Yeah. How do you know when it's going to show up twice?
I wouldn't know. Yeah, I mean, I would try all of them, but I guess like either one of my answers shows up twice, or maybe 3 times or whatever, or maybe I had an answer with like a square root of 2 in it that would never have shown up on this radar anyway.
The only reason I thought of it was because of yesterday.
If you factor that depressed polynomial, would you come up with?
Yeah. So let's factor the depressed polynomial and see what we get. So g of x is equal to 2x squared minus 5x minus 3. I'm going to set that equal to 0. And notice that all of the same analysis applies. The degree of this depressed polynomial is 2. So I know that this depressed polynomial actually contains the other two zeros that I'm looking for. All right? And my initial analysis on this one applies where I know that one of those is still going to be positive and one of them is still going to be negative. All right? Although I could technically P and Q this whole situation here. Maybe that would be interesting. Like I'm saying I could re-P and Q it. I could redo and do plus or minus 1, plus or minus 3. And I could do Q is plus or minus 1, plus or minus 2. And research through it. And it would narrow my search down a little bit. But I would still end up having to realize that I had to try 3 again. But that's a possibility. But let's just factor it straight up. So 2x squared minus 5x minus 3 set equal to 0. To factor this, what am I going to have to do? No, I can't GCF without making lots of fractions. I think AC is what we'll have to do because this leading term is there. So AC is negative 6. Factors of negative 6 are 1 and 6, 2 and 3. Which of those will subtract to be 5? So that's the 1 and the 6. So now we'll split the B term into two like terms whose coefficients are the factors we just found. Right, so I'm splitting that B term. And what signs should I have for these? Yeah, the signs are different because they multiply to be negative here. And they add to be a negative, so the more influential one must have been the negative one. Good. And now I can factor by grouping, so I'll yoink, a yoink, steal an x out of those, a yoink, steal a negative 3 out of those, and I will have x times 2x plus 1 minus 3 times 2x also plus 1. So I end up with 2x plus 1 times x minus 3 equals 0. And now that I have this factored, I can set each factor equal to 0 and solve. So 2x plus 1 equals 0, and x minus 3 equals 0. And I'll end up with x equals negative 1/2 after I do some work, and x equals positive 3. So we can see that that 3 did show up twice, in fact. And if I'd wanted to write the original factors of the polynomial, these two and x minus 3 again would have been them, right? So the original polynomial, if it mattered to us, if we were told to, would have been 2x plus 1 times x minus 3 squared, because this factor of 3 showed up twice. That's the situation there. So kind of sneaky on this problem for sure. And since this is even, this exponent, do you guys remember graphically what that means for the point 3? Anybody? What is our graph going to do at the x-intercept 3, since this is an even number? Let's see, so I'll have negative 1, 2, 3. Now let's see, yeah, let me just graph this for fun. So end behavior I knew was this and this, right? I know that it has one x-intercept at negative 1/2. And yeah, it's one of those ricochet situations. Let's see, so it's going to go like, man, it's an ugly graph, but the basic gist of that is going to be that. I mean, technically, I could even find what the y-intercept is and everything else, but yeah. So because that's an even, it's a ricochet. where when an exponent is odd, that factor gives us an x-intercept that passes through the x-axis rather than bouncing off of it. Right? So you don't have to know that fact. That's analysis for a course of much greater difficulty than this, but I don't know. I don't mind foreshadowing. All right, so there was that problem. Pulling in all sorts of analysis on it. What do you guys say? What is another good one? 29?
Yeah.
29's got a placeholder, I see. Let me grab a snapshot of this. And I think I might fit it over on the right-hand side here. Paste. And I love it when my computer is acting. All right, I need to hit that X button, but there it goes. I was like moving to close that thing, and then it would like shift back up on me. Sneaky. All right, so let's see. Let's do some mind our P's and Q's here. 36. 36, I believe, has the most factors of any number up to 36. Where our list is going to be longer than any other number below 36, like between 1 and 36. So it's a lot. And actually that's related to the reason why there's 360 degrees in a circle instead of like 365, is that the number 360 has so many factors to it that it's really divisible, right? So if I wanted to like divide a circle into 8 parts or 10 parts or 12 parts or 16 parts, like it divvies up super nice because the number 360 is really divisible. So, I don't know, little fact there. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6. Wow. Still going. Let's see, 4 goes into it 9 times. 3 goes into it, what's that? 12 times. 2 goes into it 18, and then 36. Oh, I needed a plus or minus on that 36. Man, that's a list. Although, this list is noticeably smaller than infinity. So that's good. We did narrow it down quite a bit for ourselves. And then, fortunately, on this problem, they happen to only give us a Q value of 1 there. So it's not like I have to pair these up with, 3 things and then triple the number of responses. So that's good. And I'm thinking, let's see. So we're expecting a total of 4 separate answers here. And I'm thinking it might be helpful to do Descartes in this case. And even if, we don't have to do it for this problem, but even if you just check the positive number, so let's see, that's 1 and 2, it can be helpful just to help narrow it down. Like the positive Descartes one is easy to check because I don't have to change anything. I just count the signs, right? The negative one requires a little bit more work because I have to figure out what is t of negative x. So it'd be positive x to the 4th, negative 13x squared, positive 36. Oh, it happens to be the same thing, right? 1 and 2. So 2, 2, 0. Or, what's another possibility? 0, 2, 2. Or 0, 0, 4. Or 2, 0, 2. So this one's got, right, I had to try every combination of 2 and 0 and 2 and 0 for both positive and negative. So I mix and matched those until I had every combination represented. Question, comment?
Can you also do like 4, 0, 0, and 0, 4, 0?
Well, no, because it's going to be this number or less, right? So, yeah. But good question. And then wouldn't that just be interesting if this problem had 4 imaginary solutions? Because then I'd just be stuck. Well, actually, oh, wow. We might have to come back to this problem later today. Today's lesson is pretty awesome. And this problem, coincidentally, is one of the special cases that today we will learn how to solve using quadratic techniques. Good stuff, good stuff. So anyways, let's keep going here. That's enough foreshadowing. Trying to build up excitement for the next video. Let's see, 1, 0, negative 13, 0, 36. All right, so that's the first thing I want to point out is that, yeah, we've got some placeholders there. And let's see, so for this column we're going to try our p's over q's. And the likelihood of positives or negatives are equal, right? Because it's either 2 or 0 for each of them. So I'll just start with the positives. Good news first, right? Sort of thing. I don't know. So let's try 1. So 1 times 1 is 1, with 0 is 1. 1 times 1 is 1, with negative 12 is negative 13 is negative 12. I don't see any hope for this one. 1 times negative 12 is negative 12, with 0 is negative 12. And then negative 12 and 36 is positive 24. So that's too high. So let's try another one. Now, because this is kind of high, you don't necessarily have to try 2 next. You could be like, I'm going to try 3 and see if it maybe loops back down first. I mean, it's up to you. I'll go with 2, though. I don't know. I suppose sometimes it can be pretty steep and like really jump down from 24 units in one space. It's possible. So 2 times 1 is 2, with a 0 is, nope, 2. 2 times 2 is 4, with negative 13 is negative 9. Ooh, 2 times negative 9 is negative 18, with 0 is negative 18. There we go. So it seems to have worked out in our favor. So we found 1. We found 1 positive one. What does that tell us as far as our options according to Descartes?
You can either have 2 negatives or 2 imaginary.
Right, we're down to these situations, right? Actually, maybe I'll just do one of these. I like right, so there's at least 2 positive answers. So it would make sense at this point to keep looking for positives. And then I'd say it's a 50-50 chance whether or not there's any negatives, assuming all of these are equally likely. Right? And hopefully it's not 2 again. That would be so cool of them. Let's see. So, I don't know. I guess we'll just try 3. We'll just keep going with things. So I'll start cruising along here. So 3 times 1 is 3, with 0 is 3. 3 times 3 is 9, with that is negative 4. 3 times negative 4 is negative 12. 3 times negative, what? Wow, nailed it. Wow, score. Wow, isn't that good stuff? So, so now, what type of number would you try next? Negatives. Would it make sense to try any positives?
No, you already found it.
Right, I already found my 2, right? So let's not waste our time. Now in this case, now I've got a hunch. Sometimes, especially 4th degree or even degree polynomials, can be very symmetric. All right, where it's like a mirror image. I've got a hunch, like just based on looking at this, like because there's not many terms and it's only the even terms, I just have a feeling that negative 2 and negative 3 would actually be like a good guess. So, I don't know. And technically, that's what I should have done, is worked with a depressed polynomial off the bat, but oh well. I could always do that now, but I'll just try negative 2. I'm still working with you. Well, I guess I'll work with a depressed. But yeah, I could have really narrowed it down, and then I would have had a quadratic by now, and I could have just set it equal to 0 and found them quicker without the guess and check route, you know what I'm saying? Oh well. Negative 2 times 1 is negative 2, with 3 is 1. And negative 2 times 1 is negative 2, with negative 4 is negative 6. And negative 2 times negative 6 is positive 12, with a negative 12 is 0. So there's 1. Found it. And then, like I said, I would try negative 3. And that, I mean, I would not have expected you guys to have that instinct of thinking that this would be symmetric. That's just me being a math teacher over years of seeing these problems. So, so let's see. Let's work with this even further depressed polynomial. I've got a good feeling about this one. So let's see. Negative 3 times 1 is negative 3. That's negative 2. Negative 3 times negative 2. Bam. We got it. So I am in the situation of 2 positives, 2 negatives. And it's a beautiful thing. So I end up with x equals, I guess I could summarize it, plus or minus 2 and plus or minus 3. Right? keep my list short. And not that we had to do this, but could you tell me a factor that would have been in my polynomial? I think it was t of x, wasn't it? So could you tell me what a factor would have been? Give me one factor, somebody. X minus 3? Yep, that would be one. Could someone give me another one? X plus 3? Another one? X minus 2. And could someone else give me the last one? X plus 2. Now, I don't want you to be deceived. This x minus 3, what is the solution that pairs up with the x minus 3? The positive 3, right? I don't want you to think that the negative 3 and this negative 3 are friends. They're not. They don't get along, all right? So, yeah, the opposite is what happened there. If I have an x-intercept, then a factor will be x minus that x-intercept, right? All right, so cool. So that's two problems, two of the tougher ones from this section. We combined it with a lot of analysis from Descartes, and you also can do all of your chart analysis as well if you needed to. But, what's up?
Can you go over one with finding the imaginary numbers?
Oh, yeah.
I didn't get how to do
Did we have a problem last night that
I'm
had
not
a good
sure
one?
if they did, but I just,
I don't know, but like, yeah.
like,
It looks like 35 would have had some. Basically, to find the imaginary numbers, if I would find all my real ones first, and then if I had something like this, I would use the depressed polynomial, and I'd have to complete the square or quadratic formula it, and that would reveal the imaginary numbers when I root both sides. It would be like the root of a negative. So that you can't find them using this chart. You'd have to solve it somehow. And actually, there is a cubic formula, just like there's a quadratic formula. I think there's also a quintic, like a 5th degree. I don't remember if there's a 4th degree one. I know that some of them don't exist. But yeah, so there are other strategies as well. But today, actually, I want to write this problem down on this side over here. X to the 4th minus 13, x squared plus 36. I think I want to look at that problem later today in the next video. So anyways, all right, so we're all set here. Excellent. That was last night's homework. Bam.